Assalamu alaikum. In this video I will be suggesting some problems which can be solved depending upon the articles that have been studied in this chapter number 6 of velocity analysis. So problem 6-4 is also included a general 4-ball linkage configuration and its notations are shown in figure P6-1. So actually this is the table for the problem 6-4. So students will be solving each row from A up to N, and different data is given here. So student will be solving or drawing graphically each row and finding its instant center. All 6 instant center, of which 4 will be permanent instant center and 2 will be unknown instant center using the linear graph and using kinetic theorem. So solve each row of this table. This may include in exam, and you can for the time being leave this these last two columns RPA and delta 3 for the time being, and rest all these columns are to be solved by the students, everyone. So you can download some instruction solution manual from internet, or you can solve it yourself. If you find any problem in any row in drawing, you can personally meet and discuss with me, so no issue. After that, problem 6-5 that states that repeat the problem 6-4 using analytical method. So this is already covered in chapter number 4, so leave this problem 6-5. So first problem that you will be solving, that is 6-4, and after that problem number 6-6 that states the general linkage configuration terminology for a offset 4-bar crank slider. So problem 6-6 will also be solved by the students. So this is the table P6-2 for data for the offset crank slider mechanism, or slider crank or crank slider, both data can be applied up to this diagram. So in the problem number 6-7 that states that the analytical method has been solved in chapter number 4 and chapter number 6 there. So analytical formulas have already been applied, so that is not required. So problem number 6-4 and 6-6 are important. Student will be solving them using graphically and using trigonometric methods. Trigonometric method is also analytical method, so that can be used for verification purposes. And after that, in problem 6-8 that states general linkage of configuration terminology of inverted. So leave this problem because inverted 4-bar crank slider has not been covered. So also 6-9 leave it. 6-10 also leave it. 6-11 also leave it. 6-12 after that 6-12 is important, that find all the instant centers of the linkage shown in figure P6-5. So let us find the instant center in figure P6-5. So here this is figure P6-5. Here different diagrams are given. Actually here requirement is only to find the instant centers, and no data is given here, means the velocity of this crank, etc. But in exams you will be given the Engr velocities and various dimensions for these links, so you should be able to solve it. So I will be, for example, explaining this A diagram that is quite simple, but I will be explaining it for the ease of students. So just take screenshot of this diagram and paste it here in, for example, just in Windows Paint. Here we are required to find the instant center of this linkage. So as we can observe that here are 4 links, means crank, one is ground, so that is not shown here, so that is understood that one is actually ground link, 2 is input or crank link, and third is the coupler complex motion link. As we can observe, it is made in triangular form. It is actually a binary link but is made in the triangular form, and this is a binary link. And the fourth link is this slider, which is connected with this link number 3rd coupler link, and this is actually ground. So what we will be doing to find the instant center, as we are familiar that we will first of all be drawing for example here the linear graph. So I can just, for example, write it here. Sorry, this is instant center. We will be dividing this circle into equal number of parts, and depending upon the number of instant center, as we are familiar that this circle will be divided into equal number as there are the number of links. So here are 4 links, so this circle will be divided into 4 parts. Here, like this, and after that we will be connecting these points through straight lines, just like this. We can change its line weight. Here, for example, 3 pixels will be sufficient. So also you can change its color bit, for example red color, that will be clear. And remember, permanent instant center are shown using solid lines. So in this instant center 2, 3, these are permanent instant center. Remember, this shape doesn't need to be exactly square or rectangular shape. That may be any quadrilateral shape. Actually the purpose is just to represent the permanent instant center. So in this way, permanent instant center have been connected, means actually link 1 has been connected to link 2. This is link number 1 and link number 2 has been connected here. So instant center I1 comma 2 will be through this line, and in a similar manner instant center 2 comma 3 that will be here at this moment, that will actually be connecting link number 2 and link number 3rd, and in a similar manner link number 3rd and 4th slider. So this pin will be the instant center 3 comma 4, and this slider here, this will be, and along this slider line the instant center will be I1 comma 4, but as we observe that instant center will be located at infinity. So first of all we will be for example finding instant center 1 comma 3 for some different color, for example here, and make it in a dashed pattern like this. Just here. So now it is required to find the fifth instant center, which is unknown. That will be actually between link number 1 and link number 3, which are not directly connected. So how that will be determined? That we are familiar that instant center I1, 2 is actually located at point O2, and instant center 2, 3 is located at point A, at pin A. So what we will be doing, or we will be connecting these two instant center I1, 2 and 2, 3, means this right side trio of this triangle 1, 2, 3. So we will be extending this line in both orientations. So we will be starting here from at this moment. We will be actually be extending this line in both orientations here like this. So we can use its weight a bit thinner, so that the actual links are cleared in the diagram. So this is the line actually connecting the instant center 1, 2 and 2, 3, and after that we will be connecting the instant center, the line connecting the instant center 4, 3 and 1, 4. So as we can observe that instant center 3, 4 will be located at this pin, but the instant center 1, 4, as it was explained in the class, that will be located at infinity, because the effective rocker link, this slider which actually translates or reciprocates along this horizontal surface, this is actually equivalent rocker link of infinite length. So its effective rocker link is actually pivoted. This translating joint or prismatic joint is equivalent to a revolute joint, which is located at infinity along a line perpendicular to this slider center or slider line. Slider is actually moving horizontally, so the effective rocker center line will be perpendicular to this line. So let us we can, for example, draw here first of all the instant center I1, 4. So here that can just be shown here, for example, and this is actually instant center I one, 4. So just show it here as a representation. So actually this is actually at infinity, so I can just write it here that this instant center I1, 4 will be located at infinity. So the using other trio, instant center 3, 4 is at this pin, and instant center I1, 4. So using Kennedy theorem, the third instance center I1 comma 3 will be on this line, which actually connects instance center 3 comma 4 and 1 comma 4. So we will simply be extending the line here. In this orientation, just freehand I have drawn here. I am just explaining the method. So here the intersection is made, so here we can say that this is actually the instance center. For example, here instance center I 1 comma 3. I can write it here just. So in this way, instance center I1 comma 3 has been located at this point here. This is instance center I1 comma 3. So if you are given some data, for example the angular velocity omega 2 and the crank length O2, so the velocity, for example VA, as shown omega 2 in this orientation. So I am just briefly explaining that how you will be solving. If you are required, that you will be drawing the velocity vector VA that will be actually perpendicular to this crank and perpendicular on this instance center I1 comma 3. So we will be actually determining the magnitude of the crank linear velocity. So this is the linear velocity VA that can be made here. Just I can show it here like this. So this will be actually the velocity VA, and this angle will be perpendicular here. Sorry, here this is perpendicular, and in this way this will also be perpendicular. So the velocity vector is actually now the point A will be determined using the properties or data of the crank. So once the magnitude of VA has been found out, after that point will be shifted to this link in complex motion, link number 3rd, and the center of the same point A, which was actually common, so that point will be moving about this instance center I1 comma 3, because this is the instantaneous instance center for this link in complex motion. This instance center is actually for the link in complex motion. So we will be determining the angular velocity. So angular velocity for this link in complex motion, so angular velocity will be determined that we will be dividing the magnitude of this VA divided by the distance from A up to instance center I1 comma 3. So we can I can just write it here that omega 3 will be here. For example, I can just write it here that omega 3 will be equal to VA here and divided by A I 1 comma 3. So because V is equal to R omega, so omega is equal to V by R. So this is actually R. We can also draw the symbol of line segment here at this. So this will be omega 3. So once omega 3 has been found out, then we observe we will be determining the velocity of this pin joint at B, because this point B, actually pin B is actually common with this slider, which is actually translate on this horizontal surface, and with this link in complex motion. So we will be assuming that the common point B or the pin is now connected are located at this coupler link, and this pin is actually in pure rotation about this instant center. So as we can observe here that at this instant we can also determine the angular velocity of this link, and its magnitude has been calculated. Now the direction is quite straightforward, as we can observe here that the center of rotation for this link in complex motion is actually this. So at this stage, for example, I can show that this link is actually extended link, means this link ABC, which is link is physically or practically in complex motion, is actually in pure rotation about this instant center I1 comma 3. So actually this is an extended link. So I can just, for example, draw here just to make you a visualization here, that like this, means this is somewhat extended body, and this is the center of rotation of this body, which I have enclosed in this black color line black color. So in this way, this link ABC, which is link number 3rd, is in pure rotation about instant center I1 comma 3. So that means this velocity is actually center is on the right of this velocity V. So that means this velocity will actually be rotating this body in this orientation like this. So this is the direction of omega 3. So as we can observe, this direction is actually clockwise. So if omega is anti-clockwise, as it can be observed here, omega 2 is anti-clockwise, so omega 3 in this case is clockwise, means negative. So we will, when we will be given data of crank angular velocity, so we will be multiplying it with the magnitude with the length O to A. So we will be determining velocity VA magnitude, and we will be dividing it with the distance from we will be determining the velocity magnitude VA by multiplying O to A with omega 2, and once omega 2 will be multiplied, VA will be determined, velocity VA, and then velocity VA will be rotating about this instant center I1 comma 3, and this will become the radius for this velocity VA. So that velocity will be divided on the instant center I1 comma 3, this radius, and we will be obtaining the angular velocity in this way. So that means the angular rotation direction has been calculated at this stage. So that means this instant center B, the velocity VB will also be perpendicular to this radius B I1 comma 3. So its direction will be in this direction, exactly horizontal. So this will be actually the velocity of VB. So this will be the direction of the velocity VB, because the purpose is that this will be the radius for velocity VB. So as the angular velocity or rotation has been confirmed here at this stage using the velocity VA. So this velocity VB cannot violate this orientation or direction of rotation, which is actually clockwise, that has been calculated here clockwise and shown here that this is clockwise. So this angular velocity will also be following the same orientation because this is the same rigid or extended body. So this is also equal to omega 3. I can just write it here. This is also equal to omega 3. So in this way instant center, and at the same time I have also given here a visualization that how the data can be given and this problem can be modified and can be solved. So now actually the VB will be calculated using the formula that V is equal to R omega. So R will be equal to B I1 comma 3. So we will be measuring with the help of linear scale this distance and we will be converting according to scale and finding the length B I1 comma 3 means the distance from pin B up to the instant center I1 comma 3, and we will be obtaining this value and we will be multiplying that B I1 comma 3 distance with omega 3 which was calculated here. So we will be obtaining the magnitude of this velocity VB and its direction is quite clear, that is towards left along this horizontal line, horizontal orientation. So in this way VB has been calculated. So after that point that was actually common with this link in complex motion is now shifted onto this slider, and in this way the slider velocity will be achieved. So instant center I1 comma 3 has been used to calculate the velocity VB. So instant center I1 comma 3 has been calculated. After that, for example, we will be finding the instant center I2 comma 4. So for example, use another trio. So use some different color. For example, you can use this pink color here. Like this. Also change its weight a bit. So also make it in a bit test pattern like this. So instant center 2 comma 4 will be calculated. How? That we will be using these two trios, means 1 2 4 and 2 3 4. So these trios will be used. So as we observe that the instant center 2 comma 4 will be located on a line connecting the permanent instant center 1 comma 2 and 1 comma 4, and on the line connecting the instant center 2 comma 3 and 3 comma 4. So as we can observe here, for the case of slider, if we use for example the upper trio, then instant center I1 comma 2 is this and instant center I1 comma 4 is at infinity. So we can actually draw a line parallel to this slider axis line, or the line at which infinity instant center I1 comma 4 is located, which is at infinity. So this instant center I1 comma 2 which is located at point O2, which I have not shown here just to save time, that at infinity this instant center I1 comma 2 and I1 comma 4 will be meeting, and they will be located on the same line. So I can just draw a line parallel to this line through point A throw point O2 like this, for example. Here like this. So this line is actually parallel to this line, because this instant center I1 comma 4 at infinity will be located at this line, or this instant center I1 comma 2 will be located at this line. So these line will be meeting at infinity point, and they will be making a vertex. So in this way, so we will be using this line. So in center I1 comma 2 and I1 comma 4 line has been drawn using the Kennedy theorem. The third instant center 2 comma 4 will be located on this line. So where exactly that instant center will be located, that will be determined using the other trio, which is 2 comma 3 and 3 comma 4 permanent instant connecting line. So here we can observe this is the permanent instant center 2 comma 3, and this is the instant center which is pin B. This is the instant center 3 comma 4. So we will be drawing the line from here to here like this. So in this way, so here this will be the intersection. Here I can just mark it here like this, that this will be the intersection permanent instant center instant center at this moment. So this will be the instant center I1 2 comma 4. So I can just type it here, that will be the instant center two comma 4. Approximately, let's place it here. So this is instant center 2 comma 4. So as we have observed in the article of angular velocity ratio and mechanical advantage, so it may be required to find the angular velocity ratio as well. So as we are familiar that the angular velocity is actually the ratio of the output link angular velocity to the input link angular velocity. So here the output link, actually slider B, is has no angular velocity because it has only linear velocity, because it is translating only. So its angular velocity ratio formula cannot be applied, but in a way I can explain that the angular velocity ratio, if for example we will be considering the formula for the angular velocity from the article. So go on to some previous page here, for example. Here as we can observe here the formula for the angular velocity is equal to omega 4 by omega 2, and here in this case, if for example we want to determine this omega 4 at this stage, so I can write it here just to for clarity purpose, that for example I can type it here, that omega 4 will be equal to omega 4, that will actually be equal to O4, sorry, that will be equal to VB divided by O4 the O4 up to B, means the length of the rocker link, or VB divided by scalar length C. So actually as we can observe here, that instant center O subscript 4, this is 4 in actually I could not write well on this Windows Paint. So this O4B, this actually O4 will be located at infinity, because this slider is actually equivalent to effective rocker, which is of infinite length. The rocker length is actually infinite length, so that means O4 point is actually at infinity. So that means when VB will be divided by the infinite length, so that means omega 4 will be 0. So that means from this equation we can observe that the angular velocity ratio will be 0 in this case. So again, this fact can also be verified using the instant center 2, 4 relation, like here, that as we can observe that instant center I 2, 4 up to from O2 to 24. So as we can observe here, that this will be from O2 up to I2, 4, this will be on the numerator, and this O4 I2, 4, as we can observe that this O4 is at infinite length, and at infinite length this O4 will be on the same line of this O2. So this O4 I2, 4 will be equal to actually I can write it here just to make you understand, that I can just type it here, just write it here, that O4 I comma 4 will be equal to O to A actually I am using just mouse pad, so I am not able to write it clearly. So this will be equal to O to this will be equal to the sum of this O2 I two comma 4 like this, and plus will be equal to plus O4 and O two distance. So as we can observe that O4 is actually at infinity, so the sum of O2 I1 comma 4 means this distance plus O4 is actually at infinity, so that means O4 I1 comma 2 will be located at infinity. So in the denominator, as we can observe, there will be infinity. So in a similar manner, the angular velocity ratio will be 0 using instant center 2 comma 4 that has been verified for the case of offset slider mechanism, because this is the offset slider crank problem. So this has also been explained, the angular velocity ratio. So let us move to the next example and next problem in figure that we were going to solve here. Sorry, this figure B. So I can just copy and paste it here. So we will first of all be determining the number of links in this. As we can observe here that 1 is ground and 2 is this link, which is actually mounted on this grounded pin, and this link number 4, this is binary link, and link number 3, which is actually moving gear, and this link number 3 is actually in complex motion because this gear is actually simultaneously rotating and translating, partially rotating so it has neither pure translation and neither pure rotation, so this link is in complex motion. And link number 2, actually it is it has a fixed pivot here, so this is in pure rotation. And link number 4 is also in pure rotation, and this outer ring is actually ground, so this is fixed. So here are 4 links, so using the formula to find the instant center, that is equal to, instant centers are equal to n into n minus 1 divided by r factorial. So r is actually 2, so n is actually 4, so 4 into 4 minus 1 mean 4 multiplied by 3 will be equal to 12 divided by r is 2, so 12 divided by 2, that will be equal to 6. So there are total 6 instant center. So first of all we will be determining the permanent instant center. So as we can observe here that all pin joints are actually permanent instant center, so we will first of all we determine the permanent instant center. So here as we can observe that at point O2 means at this pin actually there are 3 links, there are 3 links. So link number 4, link number 2 and link number 1, which is actually grounded link, not shown here. So here this surface actually ground, or this outer ring is actually link number 1 or grounded link. So here 4 links are actually pivoted at this common pin. This common pin is actually connecting the 3 links, one ground, this link number 2 and this link number 4 binary link. So we can independently apply the formula to determine the instant center. Here when here is actually a multiple order joint, as we can observe here the order of joint is actually 2, order of joint is actually 2, means because here are 3 links and the order of joint concept actually states that the order of a joint is actually equal to 1 less than the number of links joined at a joint. So here 3 links are joined, so order of joint is 2. So that actually means the instant center here will be greater, means greater than 1. So instant center will be actually calculated using the formula for the instant center, which is equal to n into n minus 1 divided by 2. So here actually independently excluding this link number 3rd and this outer ring at this moment, here actually there are 3 links, means link number 4, link number 2 and link number 1 ground. So 3 links, so n is equal to 3 and 3 n minus 1 will be equal to 3 minus 1, that will be equal to 2. So 3 multiplied by 2, that will be equal to 6, and r is 2, so 6 divided by 2. So that means there will be 3 instant center. So between this ground and link number 2 and link number 4, this binary link, there are 3 instant center, and that I can just type here, for example instant center, one instant center will be equal to, sorry, first instant center, that will be equal to, I can move it here, for example, that will be equal to between the ground and the link number 2, this is instant center I1, sorry, instant center I1 comma 2 here like this. So this will be instance center I1 comma 2, means between the ground and the link number 2 there will be one instance center. The second instance permanent, in this is permanent instance center. So first of all we are actually determining the permanent instance center. So the second permanent instance center, that will be equal to permanent instance center, that will be equal to between link number 2, sorry, just move it here, for example just write it here, that instance center between this link number 2 and link number 4. So here just like this, for example, just to make it nearly a subscript like this. So here this is the second permanent instance center, will be equal to between link number 2 gear, this link number 2 fixed gear, having fixed pivot which is in pure rotation, and link number 4 this binary link which is actually connecting link number 2 and link number 3rd. So this is instance center, second permanent instance center between 2 comma 4, and the third instance center will be equal to here I can just write that will be equal to between link number 1 and link number 4. So in this way all possible combination have been made. So between link number 1 and link number 4 like this, I can just change its font size and move it here. So in this way, as we can observe, 3 instance center will be located at this common pin I1 comma 2, 2 comma 4 and I1 comma 4, and these instance center have been calculated using the formula n into n minus 1 divided by r factorial, which is actually used to calculate the total instance center in a mechanism. So 3 permanent instance center have been found out, and after that here the pin between link number 3rd and link number 4, the pin is shown here. So this is also a permanent instance center, so we can write it here that the permanent instance center I three comma 4. So this is the instance center I3 comma 4, which is between link number 3rd, this link gear in complex motion, and this link number 4 which is in pure rotation. So this pin is actually permanent instance center 3 comma 4. So in this way 4 instance center have been found out, and after that we will be determining the remaining 2 instance center. So as we can observe here that the author has mentioned here assume rolling contact. So whenever it is mentioned that assume rolling contact, that means pure rolling, means there is no slipping. So here, because this ring, outer ring, is actually fixed or stationary and is not moving, and this link number third, this actually the gear which is in complex motion, this link is actually in pure rolling, means rolling without slipping. So if slipping is possible, that the author can write it here that assume slipping contact. So that means rolling will also be there, but rolling will be with slipping, means roll slide joint will be there or the half joint. So assume rolling contact means there is no slipping. So this is actually we can say in one way that this is the full joint according to Grubler equation. One freedom joint is here. So the question is there that the fifth permanent instant center, or we can say we cannot say it the permanent instant center. This is actually the instant center which is actually changing at each and every instant as soon as this link is actually moving. So this is changing its location because the contact point actually changes at each and every instant. So this point here I can just mark that this contact point, for example here this contact point is actually the fifth instant center. So this is between link number third and link number 1. So this instant center I can just type hit here that here I can just this is actually instant center I1 comma 3. Here like this, that this point is actually instant center I1 comma 3 between link number 1 which is this outer ring and this link number third, because at the contact point this point will have zero velocity, and we are familiar that the instant center has various definition. That instant center is also called instant center of zero velocity, instantaneous center of zero velocity. So that means as in a fixed axis rotation the pivot point or axle point has zero velocity, linear velocity 0. So instant center at this point when this link number third, which when it will be in contact with this outer ring, and then momentarily that point will be stationary or it will have zero velocity. Just we can assume that the tire of a car or some vehicle is rolling on a road. When a vehicle is traveling on the road and it is in pure rolling, means one-to-one contact between the tire circular surface and the road flat surface. So the every contact point on the road is actually the instant center at that moment. So in a similar manner here the contact point has zero velocity at the moment of contact, because this link number third is in pure rolling. So this is instant center I 1 comma 3. So now remains the sixth instant center. So the sixth instant center is actually between link number third and link number 2. Behind this link number 4, behind this binary link where the contact between this link number 3 and link number 2 is taking place, means these two gears, link number 3 and link number 2, are actually in pure rolling. So here is also pure rolling. So here wherever the contact is there, there is pure rolling. So at the pure rolling point, when two gears are meshing or engaging with each other, we are familiar with the fact that the contact point of two gears or friction disc has same velocity, because if the velocity is not same at the contact point when two gears are engaged or mesh with each other, then their slippage will be occurring. So here actually the author has mentioned pure rolling, so that means there is no slipping. So the common point which has the same velocity, means instant center either can is a point in a body which between two bodies which has zero velocity. So this is one definition for the instant center that we have already located here, that here the incenter had a zero velocity between this grounded link and this link number third. So that was also the instant center. And here between link number third and link number 4, the instant center has the same velocity. So any point, if it has either zero velocity between two bodies, or it has the same velocity between two bodies, in both cases that will be treated as the instant center. So between link number 3 and link number 2, sorry, link number 3 and link number 2, the common point has the same velocity. So as I can show here in the definition of the instant center which the author has written here, sorry, I can show here. Instant center, here is the definition. The definition center is a point common to two bodies in a plane, which point has the same instantaneous velocity in each body. So here we can observe that this point, contact point between link number 3 and link number 2, behind this bar is actually same velocity contact point. So I can just mark it here. So the point will be here, somewhat here. This will be the contact point behind this bar. So this is actually contact point will be the sixth or last instant center. So instant center can be calculated in any order. So this instant center I can mark it here. Just place it here. This is instance is 2, 3 because it is the convention. The lower digit is written first while naming the instant center, and here sorry. So this is the actually instance center I2 comma 3 this point. So all 6 instance center have been found. 3 instance center were here at this common pin I1 comma 2 2 comma 4 and 1 comma 4, and fourth instance center was between link number 3rd and link number 4 at this pin. So that was I3 comma 4 fourth instance center, and fifth instance center was between this contact point between this gear number 3 which was in complex motion and this outer ring which is in grounded link number 1. So that was the fifth instance center, and the sixth instance center is actually the contact point between these two meshing gear number 2 which is in fixed axis rotation about this point O2 pin O2, and the link number 3rd which is actually rotating about this point A but is not in fixed axis rotation. It is this axis is actually this pin is actually moving, so this link number 3rd is in complex motion, and contact here is behind this bar at this point. So these points are actually in pure rolling and rolling without slipping. So this is instance center 2 comma 3 between link number 3rd and link number 2. So in this way all 6 instance center have been found out. So in the exam some data may be given. For example, you can be given the angular velocity of omega 2 and you are for example required to determine for example the angular velocity of link number 3rd. So that will be quite simple, that we can calculate here. So here the important task that can be to calculate the angular velocity for this link in complex motion means gear number 3. So the procedure I will be a bit explaining. So that will be quite simple, that we will first of all we will actually be given the angular velocity for this fixed axis rotation gear link number 2 which is actually the input link here. So its angular velocity as it has been mentioned here using symbol omega 2. So that can be assumed any value, for example 5 radian per second, 2 radian per second, any value. So this radius of this link number 2 will also be given. So we will be calculating the linear velocity v2, and v2 velocity will be for this point on the surface point. So its direction, angular velocity direction is actually counterclockwise. So I can just draw here, for example I can use this simple line here. So actually I can just show here that this will be the linear velocity. Here like this. So this will be actually, I can just type it here, that this will be actually velocity v2. So this velocity will be equal to v subscript 2 actually. So I have just written here. So this will be v is 2 will be equal to r2. So this will be equal to actually this distance up to here from the contact point up to here. This will be equal to r2. I can just type here that this will be equal to r2. So v2 will be calculated, and because this gear 2 is actually in fixed axis rotation about this permanent instance center I1 comma 2, so that's velocity, linear velocity will be calculated. After that, what we will be doing, that we will be shifting this contact point, because it has the same velocity for link number 3 and link number 2 as previously explained. So that means the contact point at link number 3 has the same velocity, which is equal to v2. So I can write here, for example, that v2 will be equal to actually the v3, means linear velocity of the contact point at this moment, same orientation and same magnitude. So the contact point omega v3, the contact point at this moment has the same velocity as the velocity of the surface point of this gear link 2. So as we can observe here, that now it is very interesting and important to find that this common point at link number 3 will be in pure rotation about this instant center I1 comma 3. Remember, don't confuse yourself with this instant center I3 comma 4. So because this instant center I3 comma 4 has not the zero velocity, so that cannot be the center of pure rotation. So don't confuse that you will be using this radius. So this radius will use of this radius of link number 3 will be wrong. So the radius, effective radius, because this point is actually in pure rotation about this instant center, so this is the actually the center of rotation, because the center of rotation must have zero velocity for the calculation of angular velocities for the links in complex motion. So this point is in pure rotation about this instant I1 comma 3. So this is actually the diameter of this link number 3, this link number 3, which is actually in complex motion. So I can write it here that omega 3 will be equal to, I can type it here, that omega 3 will be equal to v3, which is actually magnitude wise equal to v2. So v3 will be divided by the I can write it here, for example, I can just to calculate the diameter, I can, for example, I can write it here 2 or 3. For example, if we are given the radius of link number 3, if we are given, sorry, just type it a bit better, if we are given the radius of this link number 3, so diameter will be equal to 2 or 3. So we will be simply dividing the diameter, which will be equal to the distance from this point up to this. So actually I can just so this will be equal to the diameter. So omega 3 will be calculated like this. So we will be dividing the v3 divided by 2 or 3 or diameter of this link in complex motion. So in this way angular velocity will be calculated. After that we will, for example, it may be our requirement that we also determine the linear velocity of this pin mean the center of this link in complex motion, the center of this link number third moving gear which is in complex motion. So what will be the linear velocity for this? So as we can observe, the permanent in this as we can observe, this pin is also a common pin for this link number third. So we will be assuming that this common pin contact point has been shifted onto this link number third. So that means its center of rotation is here on the right side. So the velocity will be perpendicular to this line. So I can for example write it here like this, that sorry this so for example it may be the requirement that you determine the linear velocity of the center of this link is in complex motion. So in this way that will be calculated. So this is actually the velocity of the instant center I3, 4. So the same velocity of the instant. So as we can observe here, the instant center 3, 4 has not the zero velocity. It is actually moving, and its velocity I can write it here. For example, I can write it here that V I three, 4 here like this, that the velocity of this center point of this gear means the velocity of point A, or I can for example if this point is actually A, center of this link number third, so the velocity of point A will be equal to R3 means from the distance from point A up to this instant center, and multiply it by the omega 3, because this is the angular velocity of the link in complex motion. So that will be the velocity of point A. But remember that this will be the linear velocity of point A, but link number this link number 4, which is actually this binary link, which is actually connecting point O2 to A, this link has the same angular velocity as this link number 2, which is in fixed axis rotation. So this link is also, because it is pivoted at point O2, so this binary link O to A is actually has the same angular velocity omega 2, because this is this will have the different angular velocity, because this link is not actually rigidly attached with this link number 2. So link number, this binary link will have different angular velocity, and that's its angular velocity can also be now calculated here like this, that I can use here, for example, I can say the velocity angular velocity of this link number 4, which is actually playing the role of rocker link here or the output link here. So omega 4 will be equal to actually VA divided by the distance from O to A, means this complete distance from this pin up to this pin. When this VA will be divided, so this will be giving the angular velocity. So students are directed that they will be assuming some suitable data, and we will be calculating the magnitudes and orientations. So here, as we can observe, the orientation of omega 4, that is crystal clear here at this moment, say that once this is actually the velocity direction of VI3, 4 and VA. So I can write it here that this is actually the velocity of point A. This vector is actually velocity of point A. So as we can observe, now this point has been shifted on to this link, on this link number 4. So the direction it is rotating this link is actually about this point O2, because this link is in pure rotation about this point O2. So this is actually moving as I can create here the arrow symbol. So this is actually the direction of rotation of omega 4. So in this way, angular velocity orientation has also been, and this rotation, as it can shown that this is counterclockwise. So omega 4 is counterclockwise, but omega 3 as we had seen here that the permanent center was instant center I1, 3 was here. So V3 was along this line. I can just for you type it here that this was actually V2 was equal to V3 at this contact point. So this V3 was actually rotating this radius about in this orientation like this. So this was actually the angular velocity direction of omega 3, and this rotation is obviously clockwise. So that means that can be preceded with the negative sign or this way. So in this way, instant center has helped us very easily to calculate all the linear and angular velocities and direction of rotation. So this is the beauty for this technique of instant centers. Otherwise, analytically we will be taking a lot of time using the relative velocity method. So in this way these two problems have been done. So now you can move toward the third problem that will be explained in a later video. So for the moment, to make the video a bit shorter, so I will be stopping here.